Hello everyone. So let us look at how to use the anisotropy in the material to manipulate light propagation. So first of all, we need to firm up our understanding of this optical property as well. So in the earlier lecture we saw how the dielectric tensor and susceptibility is going to affect the material system. So now let us move a little bit more towards the macroscopic understanding on how the refractive index of the material is going to change, and this is going to be directional. So that means the light that you are putting inside the system, right, will interact with either the x coordinate or the y coordinate or xy plane. Let us say if z is your propagation direction, it will interact with this different refractive indices. So when it interacts with this difference in the refractive index, the propagation will be affected. In an isotropic medium you do not see this effect, because when you have an electric field, let us say Ex and Ey are its components, both Ex and Ey will face the same resistance or same dielectric constant, then they are going to travel at same speed. But now the scenario has changed. So x and y, they have different dielectric constant, so that will result in change in your refractive index as well. So when the refractive index changes, we know the speed at which the wave is going to propagate will change. So this is a single wave, by the way, right. So this is a single electric field, but then when it is moving through the system, right, you can decompose it into x and y. The x component will move relatively faster or slower to your y component. What will happen in that scenario? So what property of light is going to change? Can we do interesting functionalities using this anisotropic propagation is what we are going to see right now. Okay. So let us understand the axis, principal axes and optical axes first. All right. So if we take a material system, we can define the coordinate system something like this, right. So x, y and z. So if it is isotropic, when you rotate this we will not have any problems, right. But then if it is an anisotropic material, then you have to be very careful about rotation and the assignment of various axes here. So this x, y and z that we have, right, that we define, this will be a unique set of coordinates, right. So it cannot be a random. So we need to identify a certain coordinate system, right, so that you define this for a particular material, right. So if you take a particular material system, you define what is z, what is y and what is x, right. So we need to do that, right. And when we do that, then we can define these x, y and z as principal dielectric axis, or simply principal axes if it is just x, y, z, right. So if epsilon x, y, z is called principal dielectric axes, or in general principal axes, right, for a crystal. And now once you define this, let us look at the principal refraction, right. So index of refraction. So the principal indices of refraction. So we start with our system here. So epsilon x, epsilon y and epsilon z, right. So this is all our dielectric constants, permittivity across the different direction. So we can write now the displacement field simply through this So now we can also characterize this a epsilon x, y and z, right, as a tensor. So we could write this as epsilon x over epsilon, that is a relative permittivity naught, and epsilon z by epsilon naught. So these are all the eigenvalues of the dielectric constant tensor, right. So this is nothing but, so this is the eigenvalues of the dielectric constant tensor, right. And these are all called principal dielectric constants, right. This is called dielectric constants. So the moment you define this principal dielectric constants, you can clearly easily define principal refractive indexes, right. Principal refractive indices. So that is given by nx, ny and nz. So it's nothing but epsilon x over epsilon naught, and here epsilon y over epsilon naught, and here epsilon z over epsilon naught. So now we have three different refractive indexes, right. So we all know that the speed of light is also going to change. So now if you look at the phase velocity of light, right, is now c naught over nx. So now cy is c naught over ny. Sorry, cz is nothing but so you can see here how change in the property as a function of orientation is affecting the refractive index and your light propagation. So because you have change in the dielectric constant, right, epsilon, so is your susceptibility as well, right. So your epsilon and chi are related anyways, right. So now you can define the principal dielectric susceptibility. So now principal dielectric susceptibility are defined as a function of position now. So this is all turning out to be expanding everything that we understood so far, right. So if you have a system that has anisotropy, then the material has a very strong interaction with the field that is propagating through the medium. Okay. So let us look at a very simple case. Okay. I take a material that has 2 coordinates here and then z. So now this has nx, you have ny, and this is nez, let us say, right. So now for all practical purpose, the direction of propagation is z, right. So the refractive index along the direction of propagation is not going to affect my propagation, right, all the electric field now. Now I have two refractive indexes nx and ny. Based on the orientation of my electric field, the light is going to travel either faster or slower, right, in this principal axis, right. and this would result in a system that has 2 refractive index in one medium, right. So that means 2 refraction in one medium, and this phenomena is referred to as birefringence, right. So there are 2 components, right. So you have 2 refractive indices in a single medium. In an anisotropic crystal, if there are 2 components of different indices of refraction, we could call this as crystal, okay. And this phenomena is called birefringence, all right. So this is a very important understanding from an anisotropic crystal. So when you take an anisotropic crystal and then see there are 2 different refractive indices, right, and they are going to affect the light in 2 different ways, right, and you can call that as a birefringence, right, this phenomena of 2 different refractive indices, and this particular crystal is called a birefringent crystal, all right. So the moment you have this difference in the refractive index as we saw here, right, you could come up with a way of representing this whole refractive index, right, in a very nice simple geometric way, okay. So let's look at that. So we call that as defining the index ellipsoid, right. So this the index space for all practical purpose. So let's start off with understanding that index ellipsoid, starting from the relative impermeability, right. So permittivity we know, so we start with impermeability, right. That will give us this very nice way of representing in space, right. So we call that as index ellipsoid. So how we could understand this? So the relative impermeability tensor eta can be given as eta ij is nothing but epsilon over epsilon naught, all right. So now since you are using the coordinate system x, y and z, one can write this as ij x of I eta ij x of j, which is equal to 1. So this is in a rectangular coordinate system, right. So this is what you have, and this is basically your index ellipsoid. And why we call this as a index ellipsoid? Let us just look at it a little bit carefully, right. So this is basically operating a column vector with your 3 by 3 matrix, let's say, okay. So if you do that, then what you end up, right. So if you take the material is dielectric and non-magnetic in nature, right. So it will be eta will be symmetric. So this implies eta ij will be equal to eta ji, right. And the equation that we had here, right, would become x1 square plus eta 22 x2 square plus eta 33 x3 square plus 2 eta 23 x2 x3 plus 2 eta 31 x3 x1 plus 2 eta 12 x1 x2, which is equal to 1. Alright. So this is what you would end up with. So because your epsilon is symmetric in nature, so your relative impermeability will also be symmetric in nature. So you can nicely summarize it, or deduce it into this form, right. So the index ellipsoid equation that we have here is invariant with respect to rotation, right. So if you change the orientation, right, if you rotate it at a certain angle, right, with respect to a position right in space, then whatever equation you have can still use it. So it's invariant, right. So when the coordinate system is rotated, right. So now we can look at our refractive index, how your permeability is affecting our index of refraction. So this basically, this is what you have, which is equal to 1 by n square. So similarly you can apply this to the y, which is equal to epsilon naught epsilon y, which is equal to 1 by n y square. So this is nx square. So eta z equal to epsilon naught epsilon z, which is equal to 1 by n square. So now if the coordinate system is x, y and z, then the index ellipsoid will take the form x squared or nx squared plus y squared ny squared plus z squared and z squared equal to 1. So this is how you can construct an index ellipsoid, or how the refractive index looks like inside the medium. So we started off with x, y, z, right. So let us construct that. So let's say this is z and this is y and this is x. So you have 3 different locations, right. So you have n z here, and let's say ny, and we have nx. So now you could draw ellipse around this, right. So when you do that, you will have an ellipsoid. Sorry, let me draw it thus, and you will have a circle around this, all right. So this is your ellipsoid that you have, and this is between xy plane where it is circular in nature, all right. So the nx, ny and nz, this is all principal refractive index, principal refractive indices of the crystal, right, in x, y and z coordinate system in this case, all right. So you can also rotate this, then you have to do some transformation, right. In that case your principal refractive index will will change, right, perhaps to a new value, depends on the orientation that you move, right. So, one should keep that in mind when you are doing this transformation, all right. So, with that understanding, let us look at how the light propagation, right, could be understood through this anisotropic medium, right. So, when you take any wave, right, so when you take any propagating wave, right, so you represent it as a function of position and space, right. So, position and time, right, space and time. So, this x is nothing but your electric field in x, y and z, all right. So, assuming that you are looking at a snapshot, right, and the light is propagating through along z direction, right, it is propagating along z, then what is important is, let us say the electric field will be between two components x and y, okay, because the wave is traveling like this, that means it is vibrating, right, between in x and y plane and moving in z plane, right. So, you could decompose your wave into two components, right. So, you could decompose it into x and y, and these two axes, right, Ex and Ey that you have, these fields are called normal modes, right. So, the vibration only in x is called normal mode in x, and this is normal mode or field in y. You can decompose it, you can take any wave for that matter and decompose and write it into normal modes, right. So, the normal modes are nothing but having its field in the principal axis. So, when you have field defined in that principal axis, we call that as a normal mode, okay. So, if you take a space and you have a electric field E, then you could decompose this into Ex, sorry, this is Ey and this is Ex, right. So, we will shortly see it, but this is how you can do it, and this Ex and Ey are called normal modes, right. So, let us look at how they would propagate. So, we all know that light propagates with a propagation constant. So, propagation constant is what we use to characterize wave propagation, right. So, if Ni is the refractive index along a certain direction, then your propagation constant along a certain direction I is given as Ni omega over c, all right. So, this is your propagation constant, and this is actually defining the polarization of light, okay. So, what we are primarily discussing here is what is the polarization of this light. What is polarization? It is nothing but, you know, the oscillation of your electric field in a certain plane or certain axis here, okay. So, this is what determining your polarization, right, but not the direction of the wave that is moving, right. And that is the reason why, z really does not matter, because the light is propagating in z direction, but its electric field is in x and y direction. So, x and y are important in defining the polarization, not z, okay. So, let us look at what are these normal modes, okay. So, what are these normal modes? So, normal modes are defined based on our principal axes, right. So, let's look at that. So, you could have light propagating along z direction. Let me take a thick marker here. So, you could have light propagating along here, and the electric field will be in this and then H is here. And now let us look at another scenario. Oops. And then one more scenario, let me put it so that I don't have to change again. So here it's still light still propagates through this K, right, that is your Z direction, but now the field is different now. So you have electric field in Y direction. Here we had it in X and here we have it in Y direction. And there is another scenario where light is propagating on Y, you have E here and then H in this direction, right. So these things are possible. You could have a little bit more variance as well, but based on how in which direction it propagates, positive Y, negative Y and so on, but these are all the fundamental modes or normal modes, right, that are propagating along. So where their velocity is determined by the propagation direction and the plane in which they have their X and Y field. Okay. So let's look at how we could write this wave that is propagating along X direction and Y direction, right, in the XY plane rather. Okay. So let's look at that. So you can write the light that is propagating along Z direction as x hat E of x e to the power I minus omega t plus y e to the power I k y z minus omega t, right. You can do a little bit of movement here and there, right, and eventually you can get something. Amplitude part, and then you have your phase part, right. So now the wave is propagating along X and Y direction. So this is something we saw here, right. So when you are having a wave that has a field both in X and Y, right, it is going in moving in XY plane, right, then it will have X and Y components. So now the X and Y components are defined here, and they are moving with two propagation constants, right, the wave vector along X and along Y. So this is given as this, right, the wave propagation along Z, and your ky is nothing but ky z, right. So this will be X polarized and this is Y polarized, all right. So what is the actual ky and kx is nothing but nx omega over c, and this is ny omega over c, right. So this is all propagation constant along X and Y. Okay. So this is nothing but propagation constants along X and Y. So now you could see, when there is a difference in the magnitude of X and Y, then there will be a relative difference between X and Y, right, in the movement, right. So if the light is just oscillating only in X, right, so there is a electric field that has only x component, y component is 0, right. If y component is completely 0, we call that as a linearly polarized light along the principal axis. So, no problem here, we do not have to worry about anisotropy at all, because light is, that particular electric field is not seeing the y direction. So, it is only moving in the vertical axis here, and the same thing applies if it is in the y direction, because the wave is only vibrating along y axis, right. So, whatever refractive index you have, it is uniform for the wave for y and then the x. So, these two waves are called the linearly polarized light, alright. But now things become interesting when you put the wave at a certain angle. So, now the oscillation with respect to x is at an angle, it is not in x axis. So, relative to x it has a certain angle. So, now it will induce a y component as well. So, you have both x and y. So, this is where things get interesting, because your propagation speed or propagation constant is going to be different, and they are going to travel at different speed. So, let us look at what angle these things actually make a difference, all right. So, if we take a very simple field, okay, and I put it at a certain angle, okay. If I put it at a certain angle theta, what will happen, right? Let us say, what is this angle? So, theta is nothing but tan inverse of E y over E x. So, this is from the polarization, you must have studied in your basics, right. So, this is the polarization, and it is a polarization state, right. The polarization of this would vary because it is going through this medium, right. So, polarization state will change periodically along z, and that periodicity is with a period 2 pi over k y minus k x. So, this is an important understanding from an anisotropic medium that is affecting the polarization of light, alright. So, when it is moving through a medium, it is going to change the polarization of light that is going through. So, just to give you an example, if you put a light that is linearly polarized, right, it will generate an elliptically polarized, an elliptical light, and then if you even allow it to propagate through the medium, it will become linear again. So, there is a periodicity associated with this, right. So, this will keep on repeating, all right. So, let us just quickly look at how this will happen. So, if you have x and y, we have certain theta here. So, as it propagates, it is going to create a light that is oscillating in this direction, and then rotate it this way, and it will become left, right and left polarized, and now you will come back to a completely different angle altogether. So, what this would do is it will go from a linearly polarized to another linearly polarized, but then it would have rotated by from theta to 2 theta, okay. So, you can do this, you can change or flip the plane of your linearly polarized light when you go through this anisotropic medium, right. So, in half period, the first half, it goes from linear to another linear, right. So that's the angle is now from theta to theta. So there is a special case. So there is a special case where you have this theta at 45 degrees. So when you have a light at 45 degrees, this is still linearly polarized. This gives you an interesting, it will create similar to what we saw earlier, but then the quarter wave, it will create a circularly polarized, and then this, and then you go back to 45 again, but in the opposite direction. Okay. So you go from linear to this is linear, circular to linear. All right. So this is another way of creating different type of polarization that you want based on the anisotropy that you choose, right. So let's look at what should be that length of propagation, right, of this. So that is given by very simple wave plate equation here. So let's look at that. Okay. So for a quarter wave, plate or a quarter wave change, right, that is what you go from linear to circular or linear to elliptical. So that is lambda over 4 is given by simply this, all right, or in other ways it is lambda over ny minus nx. And now for half wave, that is L lambda over 2, this 1 by 2 pi ky minus kx, which is nothing but 1 by 2 lambda ny minus nx. So this should be under modulus. All right. So this is how you can find whether you need a quarter wave conversion or half wave conversion. So integer multiple of this would also give the same thing. So it could be integer multiples should give you the same. If I have to prefer, it should be odd integer multiples, and same thing here. Odd integer multiple should give you this rotation, right, that you have in a periodic fashion. Okay. So with that we could do whatever polarization you want, and also we can change the phase of light that is going through it, right. So that is the phase retardation, right. So how can you change the phase? Let's look at how phase will be affected by this. So ny minus nx d divided by lambda. So this will give you the difference in phase, right, between when you have an anisotropic medium. So this is called phase retardation. All right. So all depends on, as you can see, the refractive index difference, right. Because of the anisotropy, you see all these interesting phenomena that you see coming from the crystals that can do polarization, rotation, phase change, right, and any arbitrary polarization that you want based on interaction of the wave with the crystal. Okay. So this gives us an additional tool from the material system that we can exploit to do a lot of interesting manipulation of waves that are propagating through this anisotropic medium. So with this we have understood all the phenomena that one can exploit using an anisotropic medium. Thank you very much.